So thank you very much for the invitation for this workshop. So today I'm going to talk about like a new approach that we have developed jointly with Dmitry Kondrashov and Michael and Jim, Pavel, and Chao Jun was also more involved for the application part. So I'm going to present like a new approach to deal with data-driven stochastic modeling. And you see that in the title there is this frequency ranked because one of the things that we're going to deal with is how to dissociate the low frequency component of your signal and the high frequency component of your signal in order to model that and recombine them. All right, so this is the outline. We're going to talk about the data representation problem, which is a very important point of this lecture today. Then I'm going to present briefly the theory that is behind the so-called data-adaptive harmonic decomposition that we have introduced. We're going to talk about first application to the Lorentz 96 model and some stochastic heat equation. And then we're going to talk about like multi-scale Stewart Lambda models. I'll explain what it is, and then we conclude on application modeling result for like simulation when data are coming from like high resolved baroclinic quasi-zero-strophic models. So let's talk about the data representation problem. So here as a motivation, you know, I picked up from this paper of Pavel Berlov, simulation of a baroclinic quasi-zero-strophic model. So to the left here, you see like an instantaneous snapshot of the upper ocean potential vorticity. And you see that here, this is in the middle is the time average of this field as time evolved. And then when you subtract, you get this AD component. And this is obtained from a direct numerical simulation, DNS, of this baroclinic QG model. So we see that we have, this is the wind-driven oceanic circulation. So we have the double gyre. Michael and colleagues have contributed, obviously, a lot on this topic. And here the model is like placed in a turbulent regime where we see the jet here. The Gulf supposed to represent the Gulf Stream or the Kuroshio, depending on the model parameters. And you have like this guy is meandering, and you have all sorts of like small eddies that move around. So the purpose is to derive data-driven stochastic emulators. But I'm not going to deal with the full model first. I'm going to consider like a coarse-grained version of it. So I'm going to, therefore, when I coarse-grain this field, I'm going to lose information and how to model this guy. So to give you a sense of the difficulty of the problem, here I picked up my coarse-grained version of my potential vorticity, and I did my EOF decomposition. And I projected just like this coarse-grained PV field on my first EOF, and this is what I get. My principal component, you see in black here, and on top of it, I have applied some smoother that will be explained later. You see that it captures some low-frequency variability that in this case correspond actually to the decadal variability that is present in this model. But you see that clearly you have a bunch of like high frequencies that are superimposed into it. And again, this is just the coarse grain. So this actually high frequency variability is like the fingerprint of, you will see that still the small eddies, even in the coarse grain level, they have their fingerprint, and they are revealed when you do your EOF decomposition into the PCs like that. So the issues, if you want to do like an inverse modeling, is that you have too many frequencies contained in this signal. And what are the practical implications? Is that if you want to do, you pick up your PCs, and you want to do an inverse model, whatever the approach you want to take, you will face the difficulty of inferring complex nonlinear functions. Or if you want to adopt like a Morris-Zwanzig approach, you will have to deal also also with complex memory effect to learn with. And if you are like an aficionados of this machine learning technique, you will have to deal with like bunch of layers and neural networks. And therefore, you will need a lot of data to learn your parameters, right? So in a certain sense, we're going to take like here an orthogonal approach. And the question that we're going to address is the following. So can we separate the low frequency component and the high frequency component of the signal? Remember that actually it's a multivariate signal, so I have many PCs, for instance, behind the signal. And the goal is to, of course, like simulate this low frequency variability and high frequency component, but while preserving a certain phase coherence between this time series. Because some theories could be like in advance of phase compared to others, and if you messed up with this, then you will get a soup. Because you see that the original feed has a coherent structures, clearly you have the jet, for instance, so you want to preserve a certain phase coherence. So this is not trivial, but this is what we will keep in mind. So let's keep this problem in mind. We'll go back at the end of my talk. But in between, you know, we're going to have fun with some math. But for that, we need always to rely on the great works. So I don't know who did that, but in '89, a certain Robert Votard and a certain Michael Gill, they come up with this singular spectrum analysis of nonlinear dynamics. And I will explain this guy to the right. So let's talk about a bit of history. This is, first of all, one of the many Michael success stories. And actually, if you look at the field of applications, I think you would need at least a big MSSA analysis to understand the distribution of and the ramification of the impact in different fields. So one day, maybe Michael will perform that, you know, or maybe a data adaptive harmonic analysis, we'll see. But just for people that are in the room, I mentioned, like, of course, there is the review paper of Michael et al. But there are like subsequent work that are very interesting, including like a revisited version of the Monte Carlo singular spectral analysis. I know that Lenny Smith has contributed on that. You might be interested to look at it. I'm sure he's aware already. And then like other recent works, of course, when you want to extract modes from data, there is a bunch of approaches, and all have their own advantages and drawbacks. And here I gave like a very, very succinct list of recent works of like the so-called the dynamic mode decomposition from Peter Schmidt. And Janikis Maida also, they did like a nonlinear SSA, so sort of, but, and then Mesic and colleagues, they worked on the Koopman mode, but there are many other approaches. But what I'm going to talk today is different from all of that. But it's clearly related to the SSA. That's why I picked up this. And now I give this advice for the students in the room. When you work on a paper, as I did many years ago, Michael handed out me this paper, you need to look for the killer formula. And the killer formula was this guy. So what is this? Cx is the autocorrelation function of your signal. Sorry, rho is your autocorrelation function Cx is the autocorrelation function of your signal. And then it acts on function rho that lives in L2. And then this operator is nothing else than a convolution, right? And this is what it is. You get actually, the SSA can be seen as a PCA in the time domain. And this is the killer formula. So it took me many years, many, to say, forget about, like, look at this formula, and to propose a new operator, integral operator. So skip all of that, go to the box. Okay, these are for like those who want to hear about math, forget about that. You look at the box here, forget about the stuff here. And then, boom, this operator, of course, I like to change notation to make things a little bit more exciting intellectually. So your phi will be essentially the Cx of Michael and Robert. Okay? My psi here is the rho of Michael and Robert. What did I change? The S is the same. The R is the T. I just changed minus S by S. Ooh. Is there anything interesting that can come out of a sign change? Actually, it's a totally different beast, mathematically speaking. The other operator is a convolution operator. This operator actually here is just a shift. I pick up my correlation function, and I make a shift. And actually, if my function psi is periodic, then it's a circular shift. And it's a left circular shift. So it's an integral operator that whose the kernel is just your autocorrelation that is read in a circular shift manner. And it acts on periodic function. So because signals are not periodic in nature, right? So what you're going to do? You pick up your correlation. You make sure that you have like enough data to resolve decay of correlation. Then you have your correlation that is almost 0. And then you're going to cheat. You're going to periodize your autocorrelation. But because you have resolved most of the information, you don't care. And then you need to change a bit the operator. But this is, again, technical. You need, like, this is the shift. And then you need to take care about, like, the boundary. But you can forget about the details here. The idea is, like, you need to resolve the decay of correlation. And here, you can do that for many cross correlation. Imagine that you have a multivariate signal. You do your cross correlations. And you build up this operator. So now, I have a bunch of these operators for each cross correlation contained in my signal. Let's say for channel I and channel J. And if you want to see how this guy deal with in the practical world, it's actually approximated by this Hankel matrix. And let's look at it. So here I pick up like the autocorrelation function that is symmetric with respect to 0. So you can pick up like just the positive part if you want, but let's use the symmetry. There's some technical advantage doing so. And then you're going to make like your circular shift. So you do your circular shift, and you see this guy now is moved over there in the second line, and this guy is moved here. And that's why you have this Hankel matrix. So you have like for each of your autocorrelation function, you have a Hankel matrix, and then you build like a block Hankel matrix, a big ground matrix C that is here. You symmetrize it to make you happy. And then you can prove that the corresponding operator of this block Hankel matrix, when you pass to the limit, of the discretization, is actually self-adjoint and compact in the space of periodic function on the torus. The circle, actually, this T is denote the circle. And therefore, you have like eigenvalues that are real, and everything is well defined. But the next object that comes out of this business is that this operator L, you will see that the spectrum of this operator L actually relates to another fundamental object that arises in spectral analysis, which is the so-called cross-spectral matrix that is symmetrized here. So this is the number of channels. Imagine my PCs. I have DPCs to represent my coarse grain QG, right? And so you take the Fourier transform of each of these guys at a certain frequency K, Fk, right? And then you form this cross-spectral matrix, like that. So what are the properties? You have a theorem here. And again, let's go to the box. You can prove that your operator L, your block-Hankel matrix operator, has eigenvalues that comes in pairs. They are all real. They come in pairs, one positive, one negative. And they relate to, they are exactly equal to what? To the singular value of this matrix, the cross-spectral matrix, at the frequency Fk. So it's very interesting because you see that among all these eigenvalues of this grand matrix formed by the block-Hankel, you're going to extract eigenvalues that can be grouped by pairs and ranked per frequency, right? And they are given by this singular spectral value. Now, what's about the modes, the eigenfunction? They are given like that for a k that represents a frequency associated with frequency Fk. And here you have the channels, you have D channels, so you have like these guys that have temporal component, and they are given explicitly like that. Very simple. Looks like Fourier. Except that here you have this theta k, that is the phase of your signal. So this stuff is giving me, the lambdas are giving me like the more or less a notion of energy contained in the signal, and the modes, they have analytic expression, and they are just there is the phase spectrum that goes into the modes. So you have your phase information, your energy information contained in this spectrum. Then you can, these are called the DA modes, and then you can do your data adaptive harmonic components, which is essentially the projection on this guy, which is obtained by this formula, and this DAX will be central in the modeling part of my story. Let's skip this, and let's go right away to applications. There is like the proof, the ideas behind the proof are very interesting. Maybe at the end I will be back on it because they are of practical relevance. So let's go to application to Lorentz 96 model, stochastic heat equation. And here I pick up two different beasts. Nonlinear dynamics, here it's time, 40 channels, classical models, no need to go on that. School example, heat equation, space-time white noise. You need to put the right scaling in front of it, like associated with the damping that is in here, right? And then you have here, you see patterns that are totally different, have nothing to do. So this is same time, this is X. And I want to look at my data adaptive decomposition, my DAD of this data. What is what? This is the frequencies that you see here, and my lambdas are now ranked in the vertical. And they are ranked per frequencies. This is the phase spectrum that you see here. And right away, you see that for those who know a bit of stochastic analysis, my stochastic heat equation is nothing else than a Ornstein-Uhlenbeck process in infinite dimension. And therefore, like if you look at power spectrum issued like in 1D, it's what is exponential decay. This is what you get here in the multivariate version of it through the DAD. And then you have here like a peak that corresponds actually, you see that there is some traveling waves that are, distorted by the nonlinear effect. And you see like here a peak, a broadband peak, and that's what you get. Now we remember the dams and the DAX. So here are the dams. My modes are organized per frequencies associated to each pair of eigenvalues. I have pairs of modes. They are organized by frequencies. And these are the DAC, meaning the projection of my data set onto these modes. So they come in pairs, the modes, and then you have these guys that comes in pairs, and you see right away that I have simplified my representation of my complex signal. Now my complex signal is the sum of these guys, essentially, multiplied by the modes. And these guys are coming in pairs. They are narrowband in frequency and modulated in amplitude. This is for the Lorentz 96. This is for the stochastic heat equation. So similar properties of the DACs, different patterns of the modes, and that's like expected because the modes depend on the phase, and the phase is different for different signals. And now that I have the DACs, so I have simplified my representation of my signal by the DACs. Now I want to model these DACs, this data adaptive harmonic component. So I'm going to skip this just to go to, again, some math, but look, focus on the, if you look at these DACs, there is like a mathematical expression, and they come in pairs. So if you like sum up this one DAC with I, the corresponding guides that comes in pairs, you have like a complex variable, and it obeys for a periodic signal. It obeys like a very simple equation, which is just like a pure oscillation. But if you have a non-periodic signals, you have boundary terms that arise here. And you have actually, so it's a periodic, like the DAX is a periodic signal plus this guy. And here you find like a convolution that involves like boundary terms of your time series. And because of the convolution that is at the frequency omega k, you have that essentially this guy is narrowband, so which is what I observed. So the inverse modeling of the DACs, then there are some analyses that I don't have time to explain here, but you have the so-called Stewart-Landau model, which is just essentially a stochastic Hopf bifurcation written in the complex domain. Here you have your cubic nonlinearities, here you have your rotation. And the noise here might depend on Z or not, might depend on the history of Z or not, or it could be just white noise. If it's white noise, it's a regular Stewart-Landau model. But if you've modeled each of your pairs of DACs by just a Stewart-Landau model like that, the problem is that you will end up with the problem of phase coherence. So you need to couple that per frequency. So at a given frequency, if you go back in like real variables, you will have here the Hopf bifurcation that you see here, and then these terms that couples the other DACs at the same frequencies. Then you have a residual. This is the noise here, and you have like a covariance matrix, and you couple them again at the same frequencies. So per frequency, you know, I have my, goes like that. I have my frequency here. I have my eigenvalues here at a given frequency. And for each of these guys, I have pairs of DACs. And so I have a model that I call multi-scale Stewart-Landau model that gives me the contribution of this frequency into my signal. And that's what you see in the blackboard. I mean, in the slides. Let's go to the modeling result, and I will conclude on that. Going back to the Lorentz 96, so you see here, to the left, the original model, and below this MSLM. I do my DAC decomposition, I extract my DACs. So you see, I have represented my signal by simpler signals that I can model efficiently using these multi-layer stochastic models. And I recombine that, and you see phase coherence. It's like the patterns are reproduced. And this is my SPDO field, and then you have, this is what you get. So you have totally different, like two models that live in totally different worlds, but using the good data representation, finding the good data adaptive change of basis, you simplify the learning of your inverse model, and I have just to go back on this guy saying that you have only few coefficients to learn here, not a lot. So I'm going to conclude on that. Let's go back to this numerical simulation of the Baroclinic QG models. Here is the DAS per watt spectrum that is much more complex than what we saw before. We can see here some modes that stand out, that actually correspond to the decadal variability, the interannual variability here. And what I can do is do my earwave decomposition. I have this decomposition that decompose my PCs by this formula that involve the DAX that you see here. And I can now simulate this psi j, which are the DAX, by my MSLM approach. And this is what I get. Not bad, isn't it? I can reproduce the low frequencies on the top. You have the original signal, right, projected on PC, like on EOF1, the PC1, the black, and here black below is the simulated signal. So I capture the low frequency variability part in cyan here and red here, and also this high frequency part. The modes, they have like an expression in the physical domain. The decadal contribution correspond actually to the jet. Now keep in mind that my modes are time dependent. Actually, they are periodic. And so these patterns oscillate in the course of time. This is the interannual variability. You see like smaller eddies that are elongated along the jet here. And this is, for instance, what I get. So to the left, I have the QG standard deviation of my model, coarse grain. To the right here, I have this multi-layer stochastic, multi-layer Stewart-Landau models reproduction of the standard variation, and I have here just a snapshot to show you that we get the right stuff. This is QG model, and here I present like latest Dimitri's result obtained on ROMS data. ROMS data are primitive equation model, much more complex, highly resolved. Here you see that this very important result that you have a string of eigenvalues and therefore a string of modes that stand out of the spectrum. And you can compress actually just by using the modes corresponding to this line here. This is your original data. This is what you can reconstruct. Here I'm not doing simulation yet. It's just reconstruction. And the colors is just to give you like a little bit of impressionism to let your imagination flow. I'm concluding on this, Mark. There is this great paper that we all know from Ruel and Takens on the nature of turbulence. And Landau and Lipschitz, as they say, as they reminded us, has proposed that turbulence was like a quasi-periodic motion with many, 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 many oscillators. Right? And they say here, and they advocate, and based on their results, that we shall see, however, that the dissipative system, like a viscous fluid, will not in general have a quasi-periodic motion. This is the so-called breakdown of quasi-periodic tori. The idea of Landau and Lipschitz must be therefore modified. So here I ask a question. We see that I have just shown to you that we can represent complex turbulent flow as a sum of stochastic oscillators embedded in the right noise bath. So indeed, maybe Landau, his view has to be adapted, but just with the right amount of noise, could maybe simulate turbulence. I don't know. But what I know is that from a quasi-periodic world with a bit of noise, maybe you can have a cow that looks like a cow. Thank you.
Quick question for Mickaël. Well, wait.
Mickaël,
yeah.
Can you summarize? So, I mean, of course, you're providing a big mathematical infrastructure for sort of one side data compression and construction of a reduced order model. So, can you summarize what is the conceptual, not the practical, the conceptual advantage of the results you propose today compared to other methods you have been mentioning during your presentation? So what is the killer element here?
The killer element is the fact that if you use many of other methods and you do a decomposition, you will see it's exaggerated, for instance, with EOF. You have bunch of other frequencies that pollute. You would like to have neat time series to infer an inverse model. So this method is harmonic in a sense and data adaptive at the same time. So it allows you to decompose your signal à la Fourier, but in a data adaptive fashion. And this gives you the elementary brick, which are these DACs, these modulated in amplitude and narrowband signals that, boom, you model with stochastic oscillators like that.
Thank you.